Okay, so we learned about angles and radian and degree measure in the last section and talked about what negative angles were. All right, so now we're going to introduce the 6 trig functions and we're going to use the triangle to introduce them. All right, and so the functions, you probably have heard of them. Maybe you don't remember how they're defined, but people typically have heard of cosine and sine and whatnot. So the 6 functions that we're going to define, the names of them at least, and their abbreviations are as follows. Cosine is COS, sine is SIN, tangent is TAN. And if you look at your calculator, if you have a scientific calculator, these are the 3 that you'll see. You won't see these guys. And the reason is they don't occur as often. And when they do occur, they're defined in terms of sine and cosine. So there's no reason to have those buttons on the calculator. They would be more or less redundant. And so secant, cosecant, and cotangent are 3 other functions, and those are their natural abbreviations. Okay, so using the context of the right triangle, let's let theta be an angle, and we're going to consider this right triangle where the adjacent side is this guy, and we're always talking with respect to theta. The opposite side to theta is this guy, and then the hypotenuse of the triangle is the side of the triangle opposite the 90-degree angle. Okay, and so by definition, from right triangle trig, these are how you define the sine, cosine, tangent, so on and so forth. Give me the angle. The sine of theta is the opposite over the hypotenuse. The cosine of theta is the adjacent side over the hypotenuse. The tangent of theta is the opposite over the adjacent. Okay. In terms of the other 3, the way you think about secant of theta is that it's 1 over the cosine of theta. The cosecant of theta is 1 over sine, and the cotangent of theta is the 1 over tangent of theta. All right, so if you remember these guys, if you remember sine, cosine, and tangent, and how these are defined, you have them all. I wouldn't remember the triangle versions of these 3 functions. They're not as natural. The typical mnemonic device for remembering sine, cosine, and tangent is this guy. It's SOHCAHTOA, right? And it represents this. The letters represent the capital bold-faced letters in this sentence. Sine is opposite over hypotenuse, so the SO. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So if you want a mnemonic device for remembering those, there you go. All right, so now I'm going to use these, right? These are the typical right triangle definitions of the trig functions. But now we're going to use the unit circle to define these trig functions with using those right triangles as our guide. And the impetus behind doing this is I want real valued functions of x that I can define for our trig functions. I want to be able to graph them in the xy plane, and so they can't just be in terms of triangles. All right, so to that end, let's take the unit circle, which is this x squared plus y squared equal to 1. And I'm going to take a theta that's, let's say, some positive angle, and I'll just draw it as though it's in the first quadrant. Doesn't have to be. But wherever that ray hits the circle, I'm going to label that as x and y. Given that it's the unit circle, the radius is 1. And the height of this triangle here, if I drop this point straight down to the x-axis to form a right triangle, the height of the triangle is y and the width is x. All right, and so given that I have a right triangle now, for theta, the adjacent side is x, the opposite side is y, and the hypotenuse is 1. So using those definitions, or using these definitions up here for that right triangle, I'm just going to apply y for the opposite, 1 for the hypotenuse, and x for the adjacent, right? That's what this triangle is. If I do that, in terms of the unit circle, I get these definitions, all right? And so for a given theta, when you find the point on the circle that corresponds to having swung around by that angle, the y-coordinate of that point is the sine of theta. Likewise, the x-coordinate of that point is the cosine of the angle theta. Once you have those, everything else is defined in terms of y and x, right? So tangent is y over x, secant is 1 over x, so on and so forth. All right, but the key to remember here is that the sine of theta is the y coordinate of a point on the unit circle, and then the cosine is the x. All right, so let's actually look at this. Let's compute the sine and cosine of some standard angles. All right, so first one, let's evaluate all six trig functions for theta equals pi over 2. Sometimes they're going to be undefined. In fact, if the bottom is 0 when you try to compute this, then we're not going to have, that function will not be defined at that angle. All right, so here pi over 2 is 90 degrees, right? And so the point xy where that radial segment hits the unit circle is up here at the point 0, 1. And so the x is 0, the y is 1. And so using these definitions right here, I know that the sine of pi over 2 is y, which is 1. So the sine is 1, the cosine is 0. The tangent's y over x, right? But x is 0, so the tangent's undefined, as is the secant because it's 1 over x. The cosecant, however, is 1 over y. That's 1 over 1, which is 1. And the cotangent of pi over 2 is x over y, so you get 0 back. All right, so it's all you really have to do here is use that observation, right? You have to know where this angle lands on the circle. That's the key. Once you know that and you have the coordinates of the point, the definitions of the trig function follows immediately. All right, another standard angle would be at pi. So at pi, you're swung around 180 degrees, so you're at the point -1, 0. And so your x is -1 and your y is 0. And so you plug those into the definition and get your sine of pi and your cosine of pi, so on and so forth. Right, so again, once you find that point, everything falls out pretty quickly. Once you get this one to go, so theta equals 2 pi, you started on the positive x-axis. 2 pi is 360 degrees, so you swung all the way around the circle, and so the radial segment at 2 pi is the same one that you started with, right? So the point of intersection is 1, 0. So the x is 0, or I'm sorry, the x is 1, the y is 0. So using our definitions, we can actually get those, and I'll swing here quick to that so you can see it right there. All right, and so if you plug those in, these are the values for your sine, cosine, and so forth. Okay, go back. Okay, what if we went the other way, right? So suppose we wanted to go negative pi over 2. Well, if you went negative pi over 2 with the circle, we're starting here and we're going 90 degrees clockwise. And so we land on the y-axis all right, but down here. So the point is at 0, -1. Notice that that's the same point you would have gotten had you went counterclockwise, but by 3 pi over 2, or 270 degrees. So those two angles kind of complement each other. All right, so let's look at that. Since the point is 0, -1, if you plug in 0 for x and -1 for y into our definitions, you get the sine, the cosine, so on and so forth. Okay. All right, now the other three that we want to do are the standard angles in the first quadrant. They're pi over 6, pi over 3, and pi over 4. The easiest one of those three to do is pi over 4, right? It's 45 degrees. But on if you went 45 degrees on the unit circle, right? So you went exactly 45 degrees, that's the y equals x line, right? That's known to be the 45-degree line. And so what we know is that at the point of intersection, when you've gone 45 degrees, this point has the same x as it does the y, right? If you're on the line y equals x, the x coordinate and the y coordinate are equal. All right, so you'll say, well, so what? Well, we know that we're on the unit circle, and so the point satisfies the equation of the unit circle, right? So if my x is equal to y, I'm just going to put x in for y here, and I'm going to plug these guys in for x and y respectively into that equation. If I do that, I get 2x squared on the left, 1 on the right, and so I can solve that for x. Just divide both sides by 2 and take the square root, right? Technically, remember, when you take a square root of both sides, you do get plus or minus. And so technically, there are two values of x for which this is true. plus or minus radical 2 over 2. But notice here we're in the first quadrant, right? And so we're going to only take the positive 1 in this quadrant. So the x-coordinate of this point of intersection is radical 2 over 2. But remember, the x was equal to the y. And so both those guys have coordinates of radical 2 over 2. All right, and so if you plug those in, the sine and cosine are both radical 2 over 2. The tangent and the cotangent are both 1. And the secant and cosecant are both radical 2. Okay, sorry about that. Okay, let's try pi over 6. So this is the trickiest one of all of them. We're going to have to form an equilateral triangle. All right, so pi over 6 is 30 degrees. Okay, so we're going to draw that in. We know that guy's 30 degrees. If we go down negative 30 degrees, right, and look at this point, that's the reflection of the point of intersection that we're interested in over the x-axis, which means the x stays the same and the y changes sign. So I know what this point is. It's x comma negative y. Okay. Now, this angle here is equal to 60 degrees, right? If you look at it just as a triangle, that's 30 degrees and that's 30 degrees. So that angle is 60 degrees. But these two angles here have to be equal because they're cut by the same transversal, right? And so that angle and that angle are the same. But since the three angles in a triangle add to 180, subtract the 60 that we know this guy is from 180 to get 120, those guys are equal, so both have to be 60. And so therefore, this is an equilateral triangle, which means all three sides have the same length. But what we know is that this side length here is 2y, right? Remember the distance formula. The x stays the same, but if you take this y minus negative y, the length of that side is 2y. And so 2y has to be 1. It has no choice because these sides are both 1 and it's equilateral. So we know that the y value is 1/2. But the minute you know the y value, you can find the x because we know the point xy has to be on the circle. And so if I plug 1/2 in for y, x comma 1/2 has to satisfy the equation of the unit circle, namely here. So I'm going to leave x in there. I'm going to put 1/2 in for y. And what I get is this equation that x has to satisfy. But if I square the 1/2, you get a 1/4. Subtract that from both sides and then take your square root. Again, you get plus or minus, but I'm in the first quadrant, so I'll use the positive one. And so the x has to be radical 3 over 2. All right, and so what that tells you is that the point P of xy, for which this angle was 30 degrees, has coordinates root 3 over 2 comma 1/2. All right, well, what that means now is you can compute the 6 trig functions because the sine is the y and the cosine is the x. And so I can use these with our definition of the trig functions to compute those guys. Okay. Pi over 3, now if you look at pi over 3, it's actually quite simple because, let's take a look at this picture. Let's see if I can enlarge this. All right, so here is pi over 6. Here's pi over 4, the 45-degree line, and here's pi over 3. Remember, pi over 3 is equal to 60 degrees. Pi over 6 was 30 degrees. Pi over 4 is the 45-degree line. It's 45 degrees. Okay? So what we can notice is the angle between pi over 4 and pi over 3 is exactly the same as the angle between pi over 4 and pi over 6. Those are both 15 degrees. And so what that tells you is that this point here that corresponds to pi over 6 and this point here that corresponds to pi over 3 have to be reflections of each other over this 45-degree line. But remember, if we reflect a point over the 45-degree line, you simply switch the x and y, right? We saw that when we computed inverses. And so this point, without having to go through an argument like we just did, you simply know that since this guy was computed to be the coordinates for that point P corresponding to pi over 6, the point for pi over 3 is just 1/2 root 3 over 2. All right, and so you can compute the trig functions for pi over 3 just using that x and that y. All right, that's it. So this section, actually, there's no homework. If I happen to have labeled a homework in the grid, just turn in the one your turn for that we did. So literally just upload that as your assignment. If I didn't, then don't worry about it. Okay, very good. We will go on to the next section in the next video. Take it easy.